Okay, so welcome to watching my hands do statistics. I hope you guys are doing well. I miss our morning stat meetings, but we can start doing this. And I sent you a post about getting together face to face on Wednesday and talking about this stuff. So I'll send you a Zoom invite. You've probably done a Zoom meeting with some of the other classes or whatever. But I'll just give you a rundown of what you read, hopefully. If you haven't read it, go back and read it. And then we'll do a couple of examples and see how much time that is. All right, so we've done this with proportions. Now we're going to do it with sample averages. And it's basically the same type of procedure. The theory's about the same, but then the end resultant formulas about how you build the distribution is just a little different. All right, so it all boils down to what is known as the central limit theorem. Right, the central limit theorem is also called the fundamental theorem of statistics. It's the central theorem of all that goes on here. All right, so what we're going to do, just like we did before, is we're going to take a population and we're going to draw good samples. So the question becomes, what's a good sample? And the answer is basically the same thing as before. It's got to be random. It's got to be not too big, 10% condition, and then it has to be big enough. We don't have success failures, so there's a little difference in that big enough thing, and I'll talk about that in a second. Okay, so if your samples are good, then if you take every single sample of a given size, find the sample averages, and make a histogram out of them, shocking, the shape of that histogram is going to be approximately normal. The center, the average of the sample averages is equal to the population average. So if we took our penny samples, took all those averages from our samples, and found their average, it would be equal to the population average. So the mean of the X bars is equal to the population mean. The spread, the standard deviation, just like with proportions, as sample size increases, the spread of your X bars decreases. And here's the formula. You take the population standard deviation, not the population mean, that should be sigma, and divide it by the square root of the sample size. So instead of using square root p times 1 minus p over n, we use this formula when we're working with sample averages. Now, in order for the conditions to get a good sample, it's got to be random. Got to pick the individuals at random, put them all in a hat, shake them up, and pick them out. And it can't be too big. You can't take a whole big chunk of the population. So you want to stay less than 10% of the population size, just like with percentages, actually proportions. But then to be big enough, it depends upon what the shape of your population is. If the population itself is approximately normal, then you can use any sample size. But if the population is skewed, the more skewed it is, the bigger your samples have to be in order to get the bell curve shape when you're dealing with your sample averages. So the rule of thumb is that the more skewed the population, the bigger the sample size has to be. But if you get to 30 or more, that's big enough to overcome almost any skewed population. So there's our conditions. Random, 10%, and population shape. make the videos too long because they get too big, and then it gets a hard time downloading them to YouTube. So I'm going to download this to YouTube and post it, and you guys can look at it. You'll be looking at it that way.